in many cases, right, it becomes necessary to model our mechanical systems as a set of springs, right? So maybe we have a table, like a milking stool, right, which has 3 legs, 1, 2, 3. So you can sit down and milk. I should label that. Milk stool. Right? So we would want to, maybe we want to model that as the top is a rigid body, and then each one of these is a spring. Something like that, right? Which then becomes, maybe we take another assumption and we're just going to give these all to a point. Right? Kind of all of our springs going to ground, and then maybe our last assumption is just all the springs are in parallel. That makes sense? So, you know, we have systems in a mechanical world where we may want to model them as a series of springs in parallel or springs in series. So we want to get an equivalent stiffness, right? So I think we kind of talked about this before. We want to find equivalent, or we want to find KEQ, right? Equivalent. That makes sense? So we want one stiffness value that's that shows how all the other stiffness values interact. Okay, so I'm just going to give you the equation. Oh, I forgot your handouts. It's all right. I'll do it next class. I'm just going to give you the equations for this, and then we're going to work back and try to show where they come from. So does anyone here play a musical instrument? Yeah, what's the first thing you do when you learn to play an instrument? I mean, like, someone gives you an instrument, like even in college, right? Freshman, you're a music major. Do you play your instrument in your freshman year? What? Yeah, there's some playing, right? No? Well, that's gonna screw over my example.
You're asking me, so you're trying to. So you have a pair of.
Well, like from an educational standpoint, right? Like if you want to play an instrument, the first thing you do is you kind of start playing around with it, right? You know, you're making noise, you're working on it, and that is not how we do engineering. In engineering, we teach you calculus and then differential equations, and we hope by your senior, you know, then solid mechanics, and then hope by your senior year, like, oh, it all clicks, but you don't remember any of your calculus, right? Yeah, because everyone in calculus says, oh, when am I ever going to use this? And then they take vibrations with me, and then they're sad. So anyways, instead of trying to do this from the math down and get to the equation at the end and have you remember, you know, oh, that makes sense. I'm just going to give you the equations, and then we're going to try to solve for them. Does that make sense? Okay. So if you wonder why I'm giving you equations, it's to try to just put them out there, and then you can see where we're building these equations from. So we got springs in series. You can also tell I don't play a musical instrument in college. I don't even know how they teach it. So we've got a mass, a particle here, right? This could be a block, a mass, but I'm just going to draw it as a particle. I'm going to label that A. Got a spring to another mass B. That's not how you draw a B in any world. Okay. To another mass C, right? And I've got K1 and K2. So K1 and K2 could be completely different, right? So if I want to find K AC, right, which is going to be my stiffness equivalent between points A and C. Does that make sense? Because KAB is just K1, and KBC is just K2. That equals 1 over K1 plus 1 over K2. Pretty easy. Right, so let's go springs in parallel. And now I've got mass, or point A, K1, good Lord. K2, B. I'm going to try to make my pencil fatter in the hope that it'll make some of this easier to read. So that's going to be K, AB, I don't know if that's any easier, is equal to K1 plus K2. That makes sense? So those are our final equations. So let's figure out how we can get there. So first, let's do our springs in series. All right. If I, oh, that's way down. Let's play a mind game here. Let's say I grab onto point C and pull it to the right. Right? What is my deflection? Yeah. So if I pull it to the right, does the deflection of K1 equal K2? Who said that? Okay. What's your name? Nick. Nick.
None of the points are fixed, but
Is it Nicholas Gunther?
Nicholas Cosma.
How do you say it?
Cosma?
Cosma? Okay. G-U-E-N? Wait.
No.
Yeah. Hello. It's
Oh, I've got two Nicholases. I don't see you on here.
I switched out your online and into your in person.
Oh, I see you right here at the bottom.
Might have to take a minute.
No, you're good. I'm sorry. I'm sorry, other Nick. I messed that up. I'll come back to you. I promise. You get the next question. How about that one? You want to do the springs in parallel? Okay. So, Nick, if I pull on C, is my deflection in K1 and K2 going to be the same?
I believe so.
All right. So what happens if K1 is stiffer than K2?
The more deflection is going to occur in K2.
Yeah. Right. So they're not always going to be the same.
Yeah.
Right. They're only the same if the stiffness is equal. So I've got a deflection AC, which is equal to my deflection of AB plus my deflection of BC. Right? Does that make sense? Does that concept make sense? Right. So whatever AC deflects, it's whatever K1 deflects and whatever K2 deflects. Right? So we can call our deflection again as stiffness K is equal to force over what? Displacement, right? So we're going to call that sigma here, right? So our stiffness K is equal to force or displacement. So if I have a displacement value, I can plug this equation or substitute this equation into here, correct? And so now I'm going to get my deflection in terms of K and F. So that becomes my force over KAC is equal to my force over K1 plus my force over K2. That make sense? See how we're substituting this equation into here and into our deflections. So what do we do with the F's? Just cancel them all out, right? We can get rid of our F's and then do a little bit of rearranging. So I'm not going to draw the 1 over F for everything. But this becomes KAC is equal to 1. That's the remnant of the F that was above it, over 1 over K1 plus 1 over K2. Right? That makes sense? Oh, what am I doing? Sorry, I wrote it there. Pretty cool, right? All right. All right. So Nick Gunther.
Hello? Yes.
Yeah. All right. So let's do springs in parallel, right? So I'm gonna go ahead and copy this. All right, so I've got two springs in parallel. So for two springs in parallel, what is our displacement? Right? So if I pull on point B, did I not label that before? That's my bad. Pretty sure you were able to figure that out. So Nick, if I pull on point B, I'm going to bring it up higher so it's on the screen. What's my displacement in K1? Is it equal to K2?
If you pull on B, it should be equal to K2, yeah.
Okay, what happens if K1 is stronger?
Then the displacement on K2 will be larger.
Yeah, I mean, like if you had a pivot in the system, but we're going to call, so when we draw these connections, we assume these connections are rigid. Does that make sense?
Okay.
So now if I pull, if K2 is stronger than K1, what is my displacement? Are they going to be the same?
No. No. If K2 is stronger.
So think about it, if I stretch this, right? So I've got I have a spring which is stretched, and this point here is rigid. Does K2 have to be the same length? Doesn't it kind of have to be the same length?
Yeah, it does.
That is a really lazy spring. Okay,
If-
that's fine. So let's say the displacements are the same, right?
Right.
So we have sigma AB is equal to sigma 1, which is equal to sigma 2, and well, that just kind of all becomes sigma, right? That becomes one value.
Right.
So if you have one value, it's kind of hard to solve for anything, right? Kind of hard to build an equation off of one value. So let's take a look at our forces. So if I have a force acting on this, right? So I've got a force AB, right? I have a force 2, and a force 1. Are those going to be the same? Assume again I've got different stiffnesses K for the same displacement. Are my forces going to be the same?
No.
No, right? Yeah, so I was just waiting for him. Yeah, so our forces are going to be different, but the sum of the forces will add up to force AB, right? So we're going to end up with force AB is equal to force 1 plus force 2, right? So again, we can substitute our equation in, K equals Fx, but we'll call it sigma here. So we end up with a sigma of KAB is equal to a sigma of K1 plus a sigma of K2. That's pretty easy, right? My sigmas are all going to cancel out. I think we can, cancel out. So that can simplify to KAB is equal to K1 plus K2. That make sense?